When we try to describe the world around us, like how fast a car is going or the pull of gravity, just using a number isn't always enough. Nope. Sometimes you need a little something more. And to see exactly what I mean, let's start with a super simple question.
Okay, let's kick things off with a real easy one. Imagine you take 2 steps forward, and then you take another 3 steps forward. So, where do you end up?
You're 5 steps forward from where you started. Of course. 2 plus 3 is 5. Simple addition, problem solved. Easy peasy, right?
Well, hold on a second. What happens if we just change one tiny little thing? Say you walk 5 steps forward, but then you turn right around and take 3 steps backward. All of a sudden, just saying 5 plus 3 doesn't work anymore, does it? The direction you're heading becomes absolutely crucial.
So to deal with situations just like this, physicists have this special little toolkit. We're going to open it up and take a look at the 2 most basic tools they use to describe the physical world, starting with one you already know really, really well. The first tool in our kit is called a scalar. And all a scalar is really is a quantity that you can describe completely with just its magnitude. And magnitude is just a fancy word for its size, or, how much of it there is.
And you know what? You're using scalars constantly, probably without even realizing it. When you buy 500 grams of margarine at the store, that 500 grams, that's a scalar. When you say it's 25 degrees Celsius outside or that it's been 10 minutes, those are all scalars. They just have a size, a number, and that's the whole story.
So, if you're going to remember one thing about scalars, remember this. A scalar just tells you how much stuff, how much heat, how much time. It answers that one simple question perfectly.
But, like we saw with our little walking problem, how much isn't always enough, is it? A scalar can't tell us where we ended up after walking forward and then backward. For that, we need an upgrade.
And that upgrade, my friends, is called a vector. This is our second, much more powerful tool. See, a vector has both a magnitude, that's our how much, and a direction, the which way. It's got both pieces of the puzzle. Think about it for a sec. A push or a pull, a force, isn't just a certain amount of effort. It's a push in a specific direction. Your weight is a force that's always pulling you down toward the center of the planet. And your car's velocity isn't just how fast you're going, it's how fast and where you're going, like 100 kilometers per hour due east.
So let's put them side by side. It's really this simple. A scalar tells you how much. A vector tells you how much and which way. One's just a number, but the other tells the complete story when we're talking about things like motion and forces.
Okay, so we get the idea, but how do we actually work with these things? How do you visualize something that has 2 different parts baked into it? How do you draw it? Well, the answer is awesome, and it's elegant, and it's simple. We draw them as arrows. And here's the brilliant part, why an arrow is just so perfect for this. The length of the arrow, that shows its magnitude. So a bigger force gets a longer arrow. Simple. And which way the arrow points? Well, that shows its direction. We call the starting point the tail and the pointy end the head.
All right, now that we can draw them, we can start to do some really cool stuff with them. Like, what if you have 2 different forces acting on the same object? What's the combined effect? To figure that out, we're going to use a really neat visual trick called the head-to-tail method.
Okay, so the name kind of gives it away, right? Head to tail. The big idea here is that we're going to chain our vector arrows together, connecting the head of one arrow right to the tail of the next one. Let's actually see how that works. Let's make this real. Picture this. Your car breaks down. You get out and start pushing it with a force of 50 newtons. Then your friend comes along to help, and they push with a force of 45 newtons in the exact same direction. So what's the total force hitting that car? Okay, so let's follow our own rules. First, we draw an arrow for your 50-newton push. Then, starting right where that first arrow ends, at its head, we draw the second arrow for your friend's 45-newton push. Just like that, we've put them head to tail.
So we've got our 2 arrows all lined up. Now what?
This is where we get the big payoff. We're looking for something called the resultant vector. The resultant it's kind of like the final answer. It's the one single vector, the one arrow that has the exact same effect as all the other little vectors combined. It's the grand total, the final outcome of all those pushes and pulls. And finding it is the easiest part of the whole thing. Seriously, you just draw one new arrow that starts at the very beginning, the tail of the first vector, and ends at the very end, the head of the last one. This big new arrow, that's your resultant. It represents the total combined force. And boom! When we measure the length of that big, final arrow, using whatever scale we set up, we find out its magnitude is 95 newtons. The total force on that car is 95 newtons to the right. See? It all adds up.
So at the end of the day, it all comes down to one thing. Direction matters. A lot. We've seen what happens when forces work together, but that leads to a pretty interesting question, doesn't it? What happens when they work against each other? Like in a game of tug of war. Something to think about.